Okay, so now we are recording, and just to make it official, I'm going to show my face again. So we will start again. Okay, so cooling systems. Okay, so that monster we have here, it's something we can find in the top of a building, on the roof of the building. So especially if we have flat roofs, we will find monsters like this. What is this? Sometimes it's difficult to tell. I think this is a cooling tower. Today we are going to explain what a cooling tower is, but it could be a chiller as well, an air chiller. I don't know. Sometimes all these things are alike. But I don't know, if we had a person here, look at this. This is like a ladder. So it's like a, I don't know, it might be like 20 or 30 feet height, this monster here. And this is a part of the cooling system. So it's not everything. It's just part of a cooling system. So when the buildings are getting larger and larger, the cooling, the heating, the cooling and ventilation systems, they are growing and they are monsters. Okay, sometimes, well, and they are not beautiful. Well, they are not beautiful. There's a kind of beauty in this machine, but it's not something that we want to show other people because it makes noise, it vibrates, it smells badly. Okay, so it's something that we have to hide, or we have to put it on the roof, and nobody has to be aware that we have these monsters on our buildings. But they are, without those machines or without those devices, we cannot breathe a good indoor air quality, an air with a good indoor air quality. So that's what I mean. So we need this to provide people with comfort, and comfort is a good temperature, a good relative humidity, a good CO2 concentration within the building, and we need all these devices. Okay, so I'm going to explain now the two systems we're going to need for, it can be for heating and cooling. Today we are going to explain cooling systems, but the systems we are going to explain now, they can apply for heating and cooling. So let's look at this. So first, we will have winter conditions, the blue rectangle, and summer conditions, the red one. We have a building. This yellow thing is the building, and the green rectangle is the heat pump. Okay, so we have indoor and outdoor conditions. In heating systems, we have to extract heat from the outdoors, and then we have to inject this heat inside. In cooling systems, we have to do the other way around. We have to extract heat from indoors, and we have to release that heat outdoors. Okay, we need to do this with heat pumps. Okay, so this would be for heating when we have a cold outdoor air at 20 Fahrenheit. Indoors, we always have 70 Fahrenheit, so it's comfort temperature. It might be different, the temperature that we have in winter than the temperature that we have in summer, but it's around 70 Fahrenheit. But outdoors, we have 20 Fahrenheit in winter, we have close to 100 Fahrenheit in summer. So what does a heat pump do? Well, it's a miracle, okay? Because we are extracting heat from the cold source, which is at 20 Fahrenheit, and we are releasing that heat indoors. And in summer, it's the other way around. We are extracting heat from the cold source, because here 70, it's colder than 100. So we are extracting heat from here, and we are releasing heat outdoors. Okay, so we are doing something that it's not natural, because usually if we have this temperature here and this temperature outside, the heat will tend to go out, and it goes out through the windows, through the envelope of the building. But the heat pump is getting that heat that we have outside, and then it's releasing that heat inside. We need electricity to do that, so that's the trick here. So it doesn't happen naturally, so we need electricity. We need to provide this heat pump with extra energy by means of electricity. But it's this is what a heat pump does. Okay, and why can the heat pump do this? Because we have this concept of the enthalpy. If you remember, we explained what enthalpy was. It's the energy that the air has. So even if it's too cold, the air has energy, and we call that energy enthalpy. Okay, so even if it's cold, if it's 20 Fahrenheit or even less than 20 Fahrenheit, we can extract energy from that air. And finally, we can move that energy from outside to inside. In summer, it's the other way around. We have to move energy from inside to outside. So that's why we need heat pumps. And heat pumps run on electricity. But it's the only device so far that can provide us with heating and cooling at the same time. Well, it's the only device that can provide us with cooling. Okay, so in summer, we have to use a heat pump. In winter, we have other options. We can burn something. We can burn pellets, wood, coal, gas, oil, whatever. We can burn something, and then we can heat up water, and then we can release that, water heat inside the building. But in summer, the only way we have to keep comfort conditions is by using a heat pump. Okay, today we are going to see a more efficient heat pump, which is the ground source heat pump or geothermal heat pump. So we are going to make the most of the properties of the ground. So the next slide is about this. We have outdoor air conditions in winter and summer. We have the building, but part of this building is buried, or it's underground, and we have a ground source heat pump there. The most important thing is the temperature of the ground. The temperature of the ground is not 20, it's not 100. It's steady over the year, and it's around 50 Fahrenheit. In winter, we are losing heat through the envelope. In summer, we are gaining heat through the envelope. So when a ground source heat pump, in winter, we are taking energy from the ground, and we are releasing that energy indoors. And in summer, we are taking that energy from the building, and we are releasing that energy to the ground. And this is the ground source heat pump. Okay, why is it called ground source heat pump? First, because it's a heat pump, so we need to apply electricity to run the heat pump. Otherwise, it's not working. Okay, so this is not natural either. So we have to apply electricity to feed the heat pump. And then it's ground source because it takes energy, or it releases energy, not to the air, but to the ground. Okay, and that's much better. We only have to look at the numbers. Here, if outside is 20 Fahrenheit, if you remember with the previous heat pump, we had to take energy from a source which is at 20 Fahrenheit. Now we are taking energy from something that is at 50 Fahrenheit. So the enthalpy of the ground is higher than the enthalpy of the air if it's too cold outside. And in summer, it's even better because we are releasing energy to something that it's colder than inside. Okay, so the outdoor air, it's warmer or hotter than the indoor air, but the ground temperature, it's lower than indoor temperature. So this is almost natural. Okay, so it has a lot of advantages doing this. In winter, because we are taking the energy of something that it's warmer than the air, so the enthalpy of the ground is higher. And in summer, we are kind of doing something natural because we are releasing heat to something that it's colder than the indoor air temperature. Okay, so that's why those ground source heat pumps are much more efficient than the air-to-air heat pumps or air-to-water heat pumps. Okay, so we have to take that into account. Is this the perfect system? Because if it were the perfect system, everybody would use the ground source heat pumps. And well, it's not. I mean, it's an option, but it's not the main option that we might find in building systems. Only, let's say, 10% of the buildings are using ground source heat pumps. We might say, why? Because it's a perfect system. It's much more efficient than others. Well, but it has other, it has cons. So we will look at it. Okay, so I want you to, I have posted here these two links to YouTube. And well, the first one explains how this ground source heat pump works. And the second explains how this chiller plus cooling tower plus air handling unit works. Okay, so those are the two cooling systems we are going to explain today. We are going to explain ground source heat pumps and these chiller plus cooling towers. Okay, so let's open the first one, the first link. This one. And okay, I will voice over the video. So here they are explaining how ground source heat pumps are working. Okay, so this is what I want you to see. This is a single family house. So we tend to think that this ground source heat pump, we need large buildings to use them. No, we can use these ones in single family house, and we can have our garden here, and we can bury those pipes. So we can have this efficient system even in single family houses. But as you can see, we need different, okay, here we can explain what's inside. Okay, so here you see that we have the heat pump here inside the house. We have this coil or this closed loop with pipes that are buried 6 feet under or even deeper. And then we have the heating systems here. So here we have a radiant floor, we have a hot water tank. Okay, so this is working with water and water. So that's why we call these kind of heat pumps water to water heat pumps. We have water here through those buried coils, and we have water inside the building, either by radiant floor, water, hot water tanks. Okay, so it's water to water. And after that, we don't have those coils exposed, so we can bury them. Okay, so this is the explanation of this water to water heat pump or ground source heat pump. We have to understand this well because this is basic for all these cooling, especially the cooling systems. In all cooling systems, we will be using heat pumps. So how a ground source heat pump works? How does it work? Okay, so we have 3 loops. We have 3 closed loops. They are not open loops. We have closed loops. That means that the water circulates here, and then it recirculates, and then it circulates again. So we don't have to fill these pipes with water. No, they are closed loop, and if there isn't any trouble or problem, we don't have leaks, we don't have to fill up those pipes with water again, only the first time. So this is the first closed loop, and this is inside the building. So this is the space heating and domestic hot water. This is a water system, so it's space heating and domestic hot water. We have radiant floors and hot water tanks. Okay, so this is what those systems are. And this is inside the house. Then we have, this is the heat pump. This between these 2 dashed lines, and we have the heat pump. And here we have the outdoors. And we have this pipe, this loop, another closed loop. This is buried. This is underground. And well, so there's another closed loop here. Okay, and finally here we have another closed loop, but this closed loop is not filled with water. We have to talk about the fluids here. So in this one, the loop that it's inside the house, we have water. So that's why we have water systems here. Here, outdoors, we have water plus glycol. This is to avoid freezing. Okay, so it's water, but we have something that prevents water from freezing. So that's why we have this glycol. That's another fluid, but we can say that it's water as well. But here we don't have any water. In this closed loop here, we have this refrigerant fluid, which is not water. It's those refrigerant fluids, they have weird names like CHF 400 and 2000 and whatever, I don't know. So they have letters and numbers. So those are weird. So we're not studying these kind of fluids. This is something that mechanical engineers do because they have to make the most of this refrigerant fluid. Where we architects, we're not dealing with this kind of fluids. We are dealing with the device itself. So for us, this is a box, and this box has four different pipes. So this is the outlet and inlet from the water space heating or domestic hot water system. We have this inlet and outlet from the ground array or the ground source, the ground pipes. And inside we have two elements. We have four elements actually. It's four. We have the compressor, we have the expansion valve, and we have the evaporator and the condenser. Okay, but through this closed loop, we don't have water. We have this refrigerant fluid. Okay, so let's move it again, and this is what happens. Okay, so first there will be we will study this the first closed loop that will be inside the house, and then this is the second one. This is the ground array. So the ground array goes from the heat pump to the ground, and then it returns to the heat pump again. And this is the inside the heat pump. This is the evaporator, and the other one would be the condenser. And here we have refrigerant. Okay, the fluid that we have in this loop is refrigerant. Okay, we zoom out. And now we are looking at this component of the heat pump. This is the compressor. So the compressor compresses the refrigerant fluid. And after that, it goes to the condenser. Okay, so this fluid, it's a gas at the beginning, and it turns into a liquid. It's not water, it's a liquid. And finally, we go down and we have this expansion valve. But this is within the heat pump. Okay, and then this expansion valve releases that fluid, and it goes to the evaporator again, and this fluid evaporates here, and it goes to the compressor, and then it condensates in the condenser, and we have this closed loop. Okay, so this is what a heat pump is about. So all heat pumps that we might find in the market, we have a compressor, we have an expansion valve, we have an evaporator, and we have a condenser. This is a heat pump. Sometimes we have the evaporator in the condenser, not in the same unit, but in different places. So this is a split system. We explained what a split system was, but in the split system, one of the components is the evaporator and the other one is the condenser. And the compressor and the expansion valve, they are somewhere. It can be either close to the evaporator or can be either close to the condenser. But a split system, it's a heat pump in which we have these two components in different places. In other heat pumps, we have these two components in the same box. Okay, so this is how the ground source heat pump works. I told you that this is more efficient because we are releasing heat, or we are taking heat in winter, or we are releasing heat in summer to the ground, and the temperature of the ground is better because it's steady throughout the year. It doesn't change. And well, that's why we are making the most of the electricity that we use to run this ground source heat pump. Okay, so this is that video. So watch that video, because I think you have to watch the video again, and you have to listen to the speaker of the video, because they will explain what all these parts or these components are and what they are doing. And then we are going to, well, we will watch the second video with the chiller and the cooling tower later, because now I want to go over the ground source heat pumps again. We can have those ground source heat pump with this closed loop that are shallow. We have these deep boreholes. Okay, so when we bury those holes around 550 to 250 feet, so this is the depth. This is what we these are ground source or ground bore holes. Okay, so this is the depth. We can have shallow pipes, but this is more efficient. It's more efficient, but it's more complicated and it's more expensive. So that's why we don't have this everywhere, because it's something expensive. But in terms of efficiency, and this is what we are looking at in this course, the ground boreholes are more efficient than the shallow pipes that we can have like 6 to 10 feet depth. If we are working with those boreholes around 200 feet, the depth, it's much better. And it's working in winter and summer. So in winter, it's taking energy. So here the arrows are going in this direction. So it's taking energy from the soil. And then in summer, it's the other way around. We are releasing energy in the soil. Okay. And why are we doing this? Well, this is a graphic about the ground temperature. And that happens everywhere. I mean, this is not happening only in cold countries or no, it happens everywhere. So there is a point at which the temperature is constant throughout the year and it doesn't change. This is the surface temperature. So the surface temperature of the ground changes. It's cold in winter and it's hot in summer. But if we move, this is in meters. So after 40 or 50 feet, this is 15 or 20 meters. So after or below 40 or 50 feet, we can say that the ground temperature, it's like constant throughout the year. And that's good, because we know that whatever happens here, the temperature is not going to change. In winter, the air temperature is going to be very cold. In summer, the air temperature is going to be too hot, but the ground temperature as of 40 feet, it's the same throughout the year. And this is what we need. Okay, so that's why those boreholes are more efficient than if we bury this loop or this just up to 10 meters. It's around 30 feet. Okay, so from 0 to 30 feet, it's good, but from as of 50 feet, it's much better. So that's why the recommended depth here, it's around 150 to 100 feet. Okay, so this is the ground source heat pump. We have this closed loop here, buried. We have the heat pump here with the evaporator and the condenser, with the expansion valve and the compressor somewhere. And then we have the other closed loop, and we can connect this to anything. In this case, this is connected to the air handling unit. And then the air handling unit, we have ducts to release the air, and then we have the return. Okay, so we have the supply and then the return. But we can connect this to radiant floors, radiators, anything that runs on water. So here we have a cooling or heating coil, and we can connect this air handling unit to the ground source heat pump. Or we can use this, we can have a radiant floor, or we can have fan coils, radiators, everything that uses hot water or cold water to heat up or to cool down something can be connected to these ground source heat pumps. And we have those boreholes in this case. So we are going down, and the depth of these boreholes can be, yeah, I told you, around 200 feet. So those are different ways to do this. We can have horizontal coils. This is what we see in the video. It's good, but it's not the best option. Then we have these horizontal closed loops. There is not, well, those are shallow systems, so they are not deep systems. So the efficiency of these and these are, it can be the same, but when we are getting deeper, the efficiency of the heat pump increases, so it's much better. And this is the best way, okay? So this is, I'm going to zoom in here. This is not a closed loop. So here we have a source of water. It can be a lake, or it can be underground water, or it can be a river, or the sea, something like that, okay? So we have a lot of water here. We don't need a closed loop here. So through this vertical closed loop, we go down and then we go up again. So it's closed. But this is not closed. We are releasing water, and then we are taking water from here. This is more efficient. It's easier because we don't depend on those loops and those pipes. It's complicated. Here, we don't have to complicate things. We only, if we have this source of water close to the house or the building, it's quite easy. But the problem is that, I don't know in the United States, in New Hampshire, there are a lot of lakes, there are a lot of rivers. There are rivers, but lakes, there are a lot of them. And there are a lot of houses with waterfront. So are they using this kind of open loop systems? I don't know. In Europe, this is forbidden. And in some, why is it forbidden? In theory, because we are not, we are taking water from this, and we are releasing water from our house. We are releasing water here. This house doesn't have to be contaminated, or just in case. In Europe, everything is forbidden, just in case. I don't know. I have to find out whether in New Hampshire this is allowed or not. It's more efficient, but anyway, if it has to be a closed loop, the only thing is that the money that we have to pay up front, it's we have to pay more money than with these open loop systems. I'm sure that it depends on the state. So in the United States, there will be different regulations depending on the state. In some of the states, this might be allowed, or in other states, you have to use closed loops. Well, I don't know. Anyway, in terms of efficiency, the horizontal coils and the horizontal closed loops are good, but are not as good as the vertical closed loop. And this is the best system. But yeah, it might be a risk that we contaminate the water. So that's why sometimes this is not allowed. Anyway, we have to find out. So this is the ground source heat pump. It's something buried here. We have a heat pump here inside the house, and then we need a heating or cooling system that runs with water. So that's it. And why is it efficient? Well, when we are talking about efficiency, we have to be aware of these two definitions. We have the coefficient of performance, COP, and we have the energy efficiency ratio, the EER. It's the same. The coefficient of performance, it's the heat delivered divided by the electric energy input. Okay, so we can say that the COP equals the heat delivered divided by the electricity. is the definition of COP, and the other coefficient, it's E equals ETR. So it's the relationship between the heat that the thermal, heat, it's this, the heat that we deliver outside the house and the electricity that we need to run the heat pump. What is this? The energy efficiency ratio, it's the same, it's the heat delivered divided by the electricity, but here we don't, we have the same units. We can talk about BTUs and BTUs, or kilowatt hours and kilowatt hours. But here we are talking about BTU hour divided by watts. So here you will find this coefficient, especially in the United States. You will find this coefficient, especially in Europe, okay? But, and values are not the same. So we don't have the same COP or the same EER. They are different. So we have to compare COP and COP and EER and EER. So we have two different devices. We don't have to compare their COPs with their energy efficiency, but we have to compare COP and this and that. Okay. Anyway, okay, so that's the coefficient of performance, and this is very important. It's the heat delivered divided by the electricity that we need to run the heat pump. So the higher the COP, the better. This is the only thing we need to understand. The energy efficiency ratio is the same, but we are comparing different units. We are comparing BTU hours with watts. Here we are comparing watts and watts. That's the only difference. And I want to show you how come, because I have been involved in, when I was an architect, in this ground source heat pumps projects. It's a nightmare because, well, as you can see, we have the, well, I've been working with these boreholes, okay? So those boreholes, we need 200 feet, and then we need to insert those pipes here. This is the head of the pipes. So as you can see, we have 4 pipes and they are connected here. So we have supply and return, and then we have supply and return. Okay, so we have 4 pipes in each borehole. We need this mass to go down because sometimes we are digging the hole, but it's not reliable. And sometimes the ground or the soil covers the hole, and we can't continue to do this. So if that happens, we have to remove the pipes, and then we have to dig again, and then we have to introduce the pipes again. So it's exhausting, and it's very expensive because you need a lot of manpower to do this. It's just for digging holes, but you need a lot of manpower and a lot of time. Anyway, after that, as you can see, we have 4 pipes, 1, 2, 3, 4, and that's each borehole has 4 different pipes, and then we have to connect all of them together, and we connect all of them together in places like this. So as you can see here, we have, this is a manifold, so we have different circuits. So this is the supply, and this is the return. So here there will be 4 pipes, 1, 2, 3, 4, and 1, 2, 3, 4. Okay, so this is 2 boreholes. If we have 4 and 4, this is for 2 boreholes. So we have 1, 2, 3, 4. So depending on how many boreholes we have, we need to complicate this. So we need a lot of pipes. So that's why it's expensive, and they have to be buried. So we have to open a trench or something like that. We have to place all the pipes here, and then we need to cover all these. So it's a lot of time and a lot of manpower, and it's quite complicated because then we have to connect all those pipes to the ground source heat pump. Okay, so that's why people are not doing this, because it's complicated. Once we have introduced the 4 pipes here, then we have to fill up those boreholes with a concrete. So add more money, more time to add the concrete here, the material itself, and then the manpower to do this. So the problem with this, it's very complicated, and it's extremely expensive. Then we have savings, we have energy savings, but again, this is not something that people can say or can be proud of. You cannot. Your client won't say, "Okay, look at this. I have boreholes, and where are the boreholes? Oh no, they are buried 200 feet under." Okay, so it's not like, okay, this is my car. Look at this. This is a Ferrari, and it's very beautiful, and you can brag about it. But here, the only satisfaction you have is the energy saving, the monthly energy savings, and because you are saving the planet. So it's there are two satisfactions here. But well, it's not something beautiful. It's not something that you see. It's something that, okay, yeah, so I'm paying less energy than my neighbor, and that's the only thing. But it's extremely complicated for the architect, for the construction company, and you have to spend a lot of money and spend a lot of time by doing this. But eventually, it pays off because it's very, very efficient. Okay, so that's why we don't have 100% of ground source heat pumps in our buildings, because it's expensive and it's complicated. And the other system, the one with chillers and the other system we are going to explain now, it's less efficient than this, but it's easier and it's cheaper. Okay, so now we are going to work with this. So we are done with the ground source heat pump. The ground source heat pump, it's something that architects want because it doesn't require, so we can have this ground source heat pump in a mechanical room, and that's it. This is all we see. The rest of the complicated thing, it's the boreholes, all the digging that we have to do for these boreholes. But if we are not aware of that, if we go to the site when everything is done, we say, okay, it's not that complicated. No, because people working on that, they have been suffering for a lot of time, and they are suffering, but they are charging you a lot of money for that. But if the money is not yours and you are not aware of the effort that it takes, this is the perfect system for architects, because the only thing we have is a box with 4 different pipes, and this is our only concern. Okay, where's the box? Here, perfect. This system is cheaper. But it's much more complicated for architects, because we are dealing with a lot of things here. We are dealing with chillers, and this chiller usually it's underground, or it's in a mechanical room that it's in the basement. And then we have the cooling power, which is on the top of the building. Okay, so we have to connect something on the basement with something on the roof. So first, we have something terrible on the roof. It's ugly. Do we want to see this? Well, this is a cooling tower, by the way, but this is a nuclear plant. Okay, but this is a cooling tower for buildings. So do we want to see something like that in our building? Not especially. But this is not all, because then we need another monster on the basement. Okay, and we have to connect these. We have a lot of pipes, so it's more complicated for architects, but it's cheaper for the client. So we have to deal with it. Okay, so now we're going to watch the second video. So if you click here on that video, you will end up watching this. Okay. By the way, those guys, those engineering mindset, they are good. I mean, well, the colors are terrible, are very ugly, but I think they explain things well, and with videos and animations and all that stuff. Okay, so first, okay, this is what we are going to study now. So we have a chiller on the basement. we have a cooling tower or a refrigeration tower. So you can, yeah, we can have cooling or refrigeration towers. It's the same. It's on the roof. So first we have to connect these two elements. We have something here on the basement. We have something on the roof. They are monsters. They are ugly. They vibrate. They make a lot of noise. So it's not something pleasant. So that's why we have to hide it. And then from that chiller, we need another system. In this case, it's connected to an air handling unit, to the cooling coil of the air handling unit, and then we can distribute the air throughout the building. Okay, so this is the schematics. We have something on the basement, we have something on the roof, we have to connect this with water pipes, then we have to connect the chiller to the air handling unit, and then we need the ductwork with air. Yeah, so we have to distribute this air throughout the building. So that's it. It's complicated and it takes up a lot of space because this is something big. So now we move on. Okay, 2:30. And here we have the two elements that we are going to see today. We have the air-cooled chiller and the water-cooled chiller. This is on the roof and this is in the basement. If we're using air-cooled chiller, we don't need a cooling tower. If we're using the water-cooled chiller, we need a cooling tower, okay? So if we're using chillers to cool down the building, the first decision that we have to make is the air-cooled one or the water-cooled one. And what is the what is the factor that makes us decide on one or the other one? Okay, so for large buildings, we are using the water-cooled chillers. Why? Because it's much better. Water-cooled chillers are the power that they can move. It's higher, and well, when we are using we are designing skyscrapers or buildings like that, water-cooled chillers are the best options. If we have medium-sized buildings like this, the air-cooled chiller, it's better. What is a large building and a medium building? It depends on the cooling load. We are talking here about therms. Okay, so we are talking more than 400 therms. You remember what a therm was? Here it's from 200 to 400 therms. Okay, so this is a medium building. It's a medium building in terms of energy, not in terms of size. Of course, size matters. So the bigger, the more energy it consumes. But well, a small building can consume a lot of energy. I don't know. There might be reasons for that. So when we are talking about large or medium buildings, we are talking about the cooling loads. Okay. So when we have large cooling loads, we need water-cooled chillers. When we have medium buildings, we can use either water or air-cooled, but air-cooled are cheaper and easier to install. So this is a better option for that. And finally, when we have small buildings, in small buildings, we don't use, in residential buildings, we don't use these air-cooled, the water-cooled chillers. We have the air-cooled ones. And even if we have a residential building, we can use split units with rooftop units and split units inside, okay? So it depends. Large buildings, water-cooled. Medium buildings, I would use air-cooled chillers. Small buildings, residential buildings, I wouldn't use even an air-cooled chiller. I would use the rooftop and the split unit. What do we have on campus in Keene State College? Well, in Keene State College, we do have, for example, in the TDS building, which is a good example because other buildings are too old. The TDS Center, it's a LEED Platinum building, so it's very efficient. It's a very good one. It's a modern building. So we have air-cooled chillers. Why? Because it's considered a medium building. It's not a large building. So but it's not a residential building, so we don't have split units. Well, we do have split units, okay? We have air-cooled chillers with air handling units, and then we have split units. We will explain in the lesson, we will explain the TDS center because I think it's worth explaining. Anyway, this is what we have to, so this is the factor that we have to make a decision whether we are using first ground source heat pumps or chillers. Well, if we have to pay, if we can pay a lot of money up front, I would use the ground source heat pump. If our client doesn't have enough money to pay up front, they will have to use chillers. Then the second decision, water-cooled chillers or air-cooled chillers. Large buildings, water. Small, medium buildings, air. This is, yeah, I think this is a good summary of this. So now we are going to explain this, pros and cons of water-cooled chillers. The pros. They are more efficient for large cooling loads. They use water evaporation to dissipate heat, so that's why they are more efficient, because this way to dissipate heat it's better than, well, it's more efficient than the other. They have higher cooling capacity than air-cooled chillers, so if we have large cooling loads, we need this cooling capacity. And that's also important, longer service life. That means that, well, things don't last forever in this world. So we have a service life. So that means that after that lifetime, we have to change the chiller and we have to replace it by another chiller. And what is a longer service life? We are talking about 20 to 25 years. The other chillers, the air-cooled chillers, they last 10 to 15 years. It makes a difference, okay? If you are the manager of the building, usually you don't have trouble during the lifetime. And if you are 50 and you install something with a lifetime or a service life of 25 years, you start thinking, okay, in 25 years I will be retired. So, but if you are 50 and you know that something is going to start having problems after 10 years, you say, 10 years, I will be 60. I will be close to retirement. And just when I'm close to retirement, the building will start having problems. Wow. Okay, so the life service, it matters, especially if you are a building manager. And you have to think about this. And then, so those are the pros. So why do we have, well, those are factors that, yeah, so, okay, let's use this. Why? Because they are more efficient, because they have a higher cooling capacity and they have a longer service life. But what about the cons? They need access to a constant supply of water. Can't use water in restriction zones. So this is something important. Where I come from Spain. The use of water, it's very important because we don't have rivers. It doesn't rain in the south of Spain. So it's we have to be careful, and you can't install things that demand a lot of water because we don't have it. Okay, so I've been working in Saudi Arabia and it happens the same. So they don't have water, but in New Hampshire it's completely different. There are plenty of water. It rains a lot. There are huge rivers, lakes everywhere. Okay, so maybe this is not a problem, but in dry countries, you might have this problem with these kind of systems because you need a constant supply of water. So if you have restrictions with water, and sometimes in dry countries, you can't use water during the night, or you can't use water from 6 p.m. to 10, whatever. So it's not a good option, this kind of water-cooled chillers. Well, they are located within the building and cause noise and vibration. well, that I think this is a con of all the heating and cooling systems. They all cause noise and vibration. They have higher installation and maintenance cost. Okay, so this is interesting. They have a longer service life, but they have a higher maintenance cost. So there's a balance between both things. They require mechanical rooms, extra risers, extra pumps, cooling towers, water treatment. So it's more complicated. Okay, so if we can avoid this, we don't use water-cooled chillers in small buildings. If we don't need a very high cooling capacity, we can get by with the air-chilled or the air-cooled chillers. We can say this, or we can study the same options or the same pros and cons for, there you go, the air-cooled chillers. Pros, the cost is something good because they are cheaper. They are not as expensive as the water-cooled chillers are. We need less pumps, risers. We don't need cooling towers, so it's easier. Look at this. This is the thing. So we have the air handling unit. This is the air-cooled chillers, and there is a direct connection between these, and both are on the roof. We don't need something on the basement. We need and then something different on the roof, and then something different here again. So we have the chiller here, and we have the air handling unit there, so we can connect both. And so there are less pipes or fewer elements like water pumps, risers, pipes. Okay, so it's easier to install. And we have less maintenance. Okay, so everything is, so those are the advantages. What are the cons? They create noise for neighboring property. Well, that's interesting. Usually we're using the building and we're not aware of what these kind of elements on the roof of the building are causing or the problems the neighbors are having because of this. Okay, so we have to take that into account. Shorter life. Because they are exposed to external weather. Yeah, so that makes sense. If they are exposed to external weather, things do not last longer. Okay, so the other one, it's on the basement. So on the basement, they are protected, and the lifetime can be about 20 to 25 years for this, 10 to 15 years for those. So we are talking about 10 years. It's a lot. And they are less efficient than water-cooled chillers. Okay, so those are the cons of this. Now, after that, okay. So this is the water-cooled, and this is the option. So we have the chiller here, water pipes, the cooling tower, and then we have more water pipes and the air handling unit. Well, so now we're going to explain this. We're going to explain the cooling tower, or what a cooling tower is. There you go. This is a cooling tower. Well, cooling tower, it's something that cools down water. So it has to be on the roof of the building. We cannot place this indoors. It has to be outdoors because it has to release heat, and it releases heat and vapor steam. So usually above the cooling tower, we see always a column of smoke. This is not smoke. This is water vapor, like this. Okay, so everything that is going out from this cooling tower, it's water, it's vapor. So it's not CO2. There are not greenhouse emissions. Okay, so in terms of CO2 emissions, we don't have to worry about cooling towers. They are just releasing water. It's like a cloud made of vapor, water vapor. But that's why it has to be outdoors. And how does it work? Well, basically, I think in this in these schematics, we can see what's going on. Okay, so this is the chiller. Here we always have a valve, we always have an expansion valve, a compressor, an evaporator, and a condenser. So we have the chiller is the same, or we have the same components we had in the ground source heat pump. So it's a chiller, it's a heat pump, but a heat pump can either heat up or cool down. A chiller only works as in the cooling mode. Okay, so it doesn't work as in the heating, as a heating device. So it only works as a cooling device. But it's a heat pump, so we have the same components: compressor, expansion valve, evaporator, and condenser. So from the condenser, we have this hot water, and we have to release the heat that we have in this hot water, and that's why we use the cooling tower. So we release that heat here, and on this cooling tower, the water cools down, so we release vapor, steam, or water vapor or steam, and then we recirculate the cool water to the condenser again. And then from the evaporator, we can, we have cold water here, and we return warm water to the evaporator, and then we have this circuit with the refrigerant, and then it refrigerates the water again. Okay, so it's the same thing we have explained with this, but instead of releasing heat to the ground, this is what we did with the ground source heat pump. We release heat with the cooling tower. And then we can use this either with a radiant floor or with fan coils, or well, something that uses water to cool down air. And this is what we have here with the air handling unit. Here we have exactly the same thing. We have the chiller. Here we don't see the evaporator and the condenser or the expansion valve or the compressor, but everything's here in that chiller. But we have this pipe going to the cooling tower with hot water. Then we release the heat, we cool down the water, and then we go down. And then from this element, we go to the cooling coil, and then we recirculate this here. Okay, we always need 4 pipes. And remember that as this is on the basement, the chiller is always placed on the basement. If the cooling tower is here, we need a pipe going all the way up to the top of the building. And then we have to go all the way down. And then from this, we have to go all the way up to the air handling unit, and then all the way down. With the air chiller, you remember that we have to connect this air handling unit to the air chiller, and that's it. But here we need a lot of pipes, a lot of water pumps, so it's more complicated. And here we have the same system, but here we have everything. We have 3 chillers, 1 cooling tower on the top, and this is the cooling system with air handling units or fan coils. Here we have boilers, and we have fan coils for heating, and we have other devices for cooling. Things are connected, so when we connect the heating circuit and the cooling circuit, there are a lot of possibilities. It complicates a lot the system, but this is, well, it's not our job to calculate this or to control this. It's about, it's not even for mechanical engineers. Controlling these kind of things for software engineers. They have sensors around the building, and they have to, okay, when is the heating system on, the cooling system on, when are we releasing heat in the cooling tower, or when are we using the boilers? Control, it's complicated. We need to understand what we are doing, and especially we need to know all these systems because we need to be aware of how much space those systems are taking up in the basement, on the roof, inside the building. So if the building is getting bigger or larger and more complicated, this becomes a nightmare because there are a lot of pipes, there are a lot of things connected. But if we divide this and if we understand what we are doing, okay, so this is the cooling system. So we have a chiller, the cooling tower, and the air handling unit. This is our cooling system. Then if you start dividing this complicated system into units that you can understand, everything is easier. The problem is that when we are dealing with the engineers, they are showing us the whole system and it's very difficult to understand. So we have to spend some time with them, asking them relevant questions so that we can, okay, so this is the cooling system. What is the heating system? So we'll understand the heating system and then we are connecting things and we have 3 chillers and 2 boilers. Why? Usually we have this for backup. Imagine that one of the boilers is broken, so the other one is working. Or one of the chillers so we have an issue with one of the chillers and we have other backup chillers. You see that for the water pumps is the same. We always have this. So usually one of the pumps is working and the other is stopped. When this pump stops working, then the other takes over and then we can replace the other one. So usually we have 2 things in parallel like this in these building systems. It makes the system much more complicated because we duplicate the devices, we duplicate boilers, we duplicate chillers, we duplicate water pumps, but at least we have a backup. So if something's wrong with one of the devices, okay, we can make sure that the building is not stopped. And so mechanical engineers, they have a lot of work, and we have to understand what they are talking about, although we are not mechanical engineers. But we need to know something about this, and at least we need to talk to them to understand what they are doing and to understand what we have to do in the building to design the mechanical rooms or to design the roof, the basement, because it affects our design, and all these pipes and ducts, it will end up affecting our design. So this is what we need. Okay, cooling systems. What's next? We have to work with schematics now. There you go. So this is another part of the assignment. So first, I will give you a statement about the building. So we have this number of people, we have air handling units, water-cooled chillers, refrigeration towers, boilers, and then you have to design a system with all these components. So I'm providing you with different examples, okay? So what is this? So we have these schematics, and then we can analyze what we have here. What we are going to do is the same. So I will provide you with a text, and then you have to read the text, and then you have to place, or you have to connect all the components of that system. But if we look at this, what do we see? What is this? This is a chiller. Is this the air-cooled chiller or a water-cooled chiller? It looks like a water-cooled chiller. If this is a water-cooled chiller, it has to be connected to the cooling tower on the top of the building. Okay, and to move the water, we need a water pump here. Okay, that's perfect. And then the other circuit, it connects the chiller to this. What is this? This is a fan coil. And the fan coil, we have a cooling coil and we have a heating coil. So the cooling coil is connected to the chiller. And what about the heating coil? The heating coil has to be connected to a boiler. So this can be a gas boiler. We have a chimney here to release the gases, to get rid of those gases. And at the same time, this gas boiler is heating up this water tank. And this water tank is connected to solar collectors. Okay, so if there's sun, these solar collectors are heating up this water tank. If there isn't any sun here, we have to connect the gas boiler to this water tank. And then we need a water pump here, and we have a shower with hot water. And what is this? Well, we need ventilation. So this is a heat recovery. We could have the air handling unit, and the air handling unit is made of a heat recovery and two cooling coils, the heating coil and the cooling coil. Or we can have fan coils inside the building, heat recoveries outside the building, and those are two different systems. Okay, so if we are using this, we have to put names on different things. So this is a water cooled chiller, this thing here. This is a cooling tower. Okay. This is a gas boiler. This is a hot water tank. Okay, this is a hot water tank. Those are solar collectors. Then those are fan coils. Coil. This is a fan coil, and this is another fan coil. And finally, this is a heat recovery. Okay, so with this system, we have everything we need. We have heating with a gas boiler and the fan coil. This is the energy production, and this is the energy, this is the terminal unit. So this is the energy producer, and this is the terminal unit for the heating system. For the cooling system, we have the water chilled, the water-cooled chiller. So if it's a water-cooled chiller, we need a cooling tower. And then what is the terminal unit? It's the fan coil. So if the gas boiler is working, we have heating. If it's not working and the chiller is working, then we have cooling. Do we have hot water? We have hot water and we have solar collectors. And if we don't have any sun, then we need a backup plan. So the backup plan is that the gas boiler is connected to the tank. So we always have hot water for showers. And then for ventilation, we have a heat recovery and we have ducts, okay? But this is schematics of a complex building with a lot of things, okay? So this we are talking about something serious here. So this is not a single family house. If we are using one of these water-cooled chillers, we know that we will have large cooling loads, and probably we will have thousands of fan coils. If it's a skyscraper with thousands of offices, we have a fan coil in each office, and there will be 5 or 10 or 20 chillers and 2 or 3 gas boilers and different tanks. Okay, so it's a question of complicating things, but this is, here we have everything we need and everything is connected. So we have a cooling tower and a chiller, we have to connect both with supply and return. If we have fan coils in the chiller, we have to connect the fan coils and the chiller. If we have a boiler and we have a fan coil, the heating coil has to be connected to the boiler. We have to we need this chimney or this pipe to get rid of the gases that we are burning here. And then we have the heat recovery systems and solar collectors. So we are sustainable because we're using solar energy here. Okay, so this is something that, well, this is a building. What are we going to do with Revit? Okay, so in Revit, we will have different spaces. So we will place different things, and we will place chillers, cooling towers, boilers, and then we will have to connect this with Revit. Okay, so by doing this with Revit, you will end up internalizing what we are doing because you actually are connecting things. I mean, so you need to know what to connect. Here in the schematics, let's say, okay, is this the basement or is this the top of the building, the roof? Is this the first floor, the second floor? If we are working with Revit, there will be a basement, there will be a roof, there will be 2 different floors, and we will have different things, and we will have to connect things on the basement to things on the roof and things on the first floor, on the second floor, so we will understand everything better. But first, we need the schematics. So in the schematics, we have different elements, and we have to connect those elements. If we connect the cooling tower to the hot water tank, we're doing something wrong. If we connect the cooling tower to the fan coil, we're doing something wrong. If we connect the hot water tank to the chiller, it doesn't make any sense. Okay, so that's why by doing this, I would realize if you know how things are working. What's this? So that's a different system. So that can be the system for a large building because we have this chiller. Here we don't have a chiller and we have a split system. So you see that we have the indoor split unit here. We have the outdoor unit here. So that means that this can be a residential building because we don't have chillers, especially if we don't have this kind of chiller. This can be a residential building. Residential buildings use split units. It's very unlikely that commercial buildings are using split units. So when we have this, we have either office buildings or residential buildings when we have split systems. And why do we have green lines here? Well, because usually we have blue for cold water. So if we are talking about the cooling system, we use something bluish. If we are talking about the heating system, we are using the red color, and blue and red are for water. If we are using refrigerant, because here we are not connecting this with water, it's a refrigerant fluid. So that's why we need this green, this green color. So what do we have here? This is for, it can be for cooling, okay, because we have a split system. So this is a heat pump. So it can provide us with heating and cooling, but here we have a heating system with a radiant floor. So we have a boiler and we are connecting the boiler to the water tank and to this radiant floor. Okay, so the radiant floor can be for the heating system. It's more comfortable, it's more efficient, a radiant floor. I like it. But the radiant floor for cooling, it's difficult. So we need an extra cooling power. So that's why we have a heat pump with a split system. We need a heat recovery for ventilation, okay? Because here we need a mechanical ventilation. We don't have an air handling unit, so we need a heat recovery here. Okay, so let's place names on this. So this is the indoor. This is the split indoor unit. We have 2 of them. This is the split outdoor unit. This is a gas boiler. Here. Okay. And this is a hot water tank. And what else? Oh, the heat recovery. Heat recovery for ventilation. Okay. What about this one? Okay, so here, do we have heating and cooling? Apparently, we have the air handling unit here with the heat recovery. When we have the heating coil, the cooling coil, and the heat recovery in the same box, this is the air handling unit. So here, this is the air supply, the air extraction or the air return, and then we need the fresh air supply here, and here we have the heat recovery. So here we have a chiller. We have thermal collectors or thermal panels. So this is for solar energy. The solar energy is connected to the buffer tank here or the hot water tank. We need something, if there isn't any sun, we need the backup. So the backup is a heat pump. So a heat pump for heating, and we have an air-cooled chiller for cooling. So those are on the roof, so they can be directly connected to the cooling coil here. Heat pump, it can be in the basement. Okay, it can be in the basement. So it's connected to the heating coil here, and then it's the ventilation, it's through the air handling unit as well. And that's it. And this is, well, this is something more complicated, and I will explain this later or next week. By the way, this is the TDS center. Okay. I don't know if you have realized that this is well, this is a part of the TDS center. So this is the office building in the TDS center. We have all these devices. I will explain that later. Okay. So this is it. Well, this is the first thing. This is the solar thermal collectors. We can have a tank, the solar thermal collectors, and a boiler as a backup. Okay, so this is but this is not for, this is just for the domestic hot water, where we don't have a heating system or a cooling system here. Okay, so we have this, and whenever we have solar collectors, a buffer tank, we always need a backup for if we don't have any sun here. We always need a gas boiler to heat up this if we need to use domestic hot water. Okay, so those are different examples of different systems, heating, cooling, and ventilation systems. But now this is the schematic diagram of the whole building. So this is not just, so we have the building here, okay? We don't know the shape of the building. We don't know how many people, we don't know the use of the building, but all the systems involved in the heating, cooling, and ventilation system of the building, or all the devices are here. And we are connecting those devices. And okay, so by looking at this, okay, now I have this building with all these devices, and I can start connecting them. Okay, the water-cooled chiller and the cooling tower. We need 2 pipes, 1 and 2. This is a PowerPoint, so you can do this with a PowerPoint. It's fine. There are other softwares that are better. And where is it? Here. Okay. I have found this eDraw. Okay, and this is the most important thing. Try it free. So you can try this for free, I think for 15 or 30 days, I don't know. And after that, you can keep on working on that. The problem is that you can't save your projects, okay? I have downloaded this software, this eDraw, and it's quite good because, where is it? This is a software for schematic drawings. There are thousands of them on the internet. I have found this, that it's for free. So that's why I'm recommending this, because it's for free. So as you can see, we have a lot of diagrams. It's not something for buildings. Okay, so you can do this. You can use this software to prepare presentations and animations. So it's something cool. But here it has the industrial engineering module. Okay, so with these things, you will find air conditioning, water treatment, cooling, and okay, so you will find a lot of blocks and a lot of diagrams that you can use for this. So I have been working with what is it? Oh, this one. Okay, it's cool. Here you have a lot of options. So there are a lot of things that you can for cooling, for heating. So there are a lot of things you can upload. But the most important thing is that if you don't find what you are looking for, you can always use drawing. Okay, so here you can create your own library, and here you can insert something. You can select images. So whatever you have on your file, okay, so if you download these kind of things from internet, so you can take it here and then you can place it on these schematics. You can reduce it. And the good thing is that you can connect things. Here you have connectors, for example, and then you can connect this element to that. Okay, and this is cool because you see that when we are overlapping different pipes, we have this symbol. So that means that it's not a cross here. And then you can select this and you can, okay, you can change the line type and the color. Okay, and we have ducts. Okay, so those are air ducts. So you can insert here, and here you can change the size of the duct. You see, by changing this, we can change the size of the duct. So this is 0.5, it's very thin, or it can be 8, it's very thick. And then we can do this. We have elbows. So we can connect this to this elbow, and then we can change the size of the elbow. So it's quite good for this kind of schematic. So that would be the chiller, that would be the refrigeration tower. So we can connect this with those connectors. If this is the gas boiler, I have connected the chiller to the refrigeration tower here, and then to the cooling coil of the air handling unit there. If I want to connect the boiler to the heating coil here, there you go. And then I can make it red if it's a red thing, and I can change here the width. of this line. Okay, and this is interesting because when we are doing this, that means that it's not across here, so they are at different levels. So this is connecting this, and it's not interfering with this pipe here. So this is a chimney. We are releasing this air from the gas boiler, and that can be a hot water tank. So this is the supply air duct, and then we need a return air duct here. Okay, so there are a lot of options you can do with this software. If you are interested in using this software, let me know, because I'm preparing a library here with all the options that we are explaining, chillers, air handling units, gas boilers, and all that, all the devices. So if you want to use this, first you have to install this one on your laptop, and if you can run it, let me know, and I will send you my library so that you can use the same things that we are using here. If you don't have this, it's not an excuse, because you always can use the PowerPoint, and with PowerPoint we can make a nice schematic as well. The other one, it's more professional, I think, but you can use a PowerPoint as well. Okay, so this is it. And just to finalize, I'm going to introduce the assignment. Okay, so that I'm going to post this assignment. It's due on October the 6th. So it's next Tuesday, so 1 week from now. But you can start doing this because you should know how to do that. We have the air handling unit here. We have 2 rooms. One room has 100 plus Y people, and the other one has 20 plus X people. X is the last figure of your ID, let's say your in-state college ID. And this is the second last figure of your in-state college ID. So that means that you should have different numbers, okay? Because you will have different people here. So the people will affect the CFM, and the CFM will affect the final cooling and heating load. Here we have a heat recovery. And this variable air volume, it's something interesting. I will go over this on Thursday because the variable air volume allows us to, here we might have 2 different rooms. And this room, it's up to 200 people, let's say. But if we have 100 people in this room and 20 people in that room, that means that if we have a variable air volume, I can control the airflow. If we don't have the variable air volume, and the maximum people here, it's 100, then we will be using 100 people here, 100 people there, and we will be losing a lot of energy. So I will explain what a variable air volume is, but well, that's the concept. You can start working on the calculations. You have to calculate the ventilation airflow, the indoor and outdoor enthalpy, the heating power in winter, the cooling power in summer, and the energy. And then you have to prepare the schematics for heating and cooling system, including pellets boiler, air chiller, refrigeration tower, and air handling units. This is option A. And option B, it's ground source heat pump and air handling units. Okay, so you can start preparing those schematics. You can start with calculations if you know how to do it, because this is the same thing we did last week or 2 weeks ago. Yeah, it was 2 weeks ago. And the 7th point, it's about Revit. So we will use Revit to, so once we are done with the calculations, the schematic drawings, then we will use Revit to finalize this. So this is due on October the 6th, but it's only this. It's only the calculations and the schematics. And then we will have 2 more weeks to work with Revit. But that will be the midterm assignment.